Okay. Right. So, it's on here. Okay, so welcome to today's data linkage anonymization seminar. There's going to be a shared talk between myself and David Hand. So this is really work in progress. And when we met this morning, we came up with new ideas and changed things. So it's going to be very ad hoc. But feel free to ask questions. So it's basically work where David and I talked in July when we had the first workshop about how do we measure the quality of record linkage systems. And David has done a lot of work on the ROC curve in the classification space and issues with that. And we believe there are similar issues happening in record linkage as well. So let me see if that works. That works. So we are going to talk a little bit about, very quickly, the linkage process and linkage quality and how we measure traditionally record linkage quality, and then we move on into the F measure and what we believe its flaws is, and that's what David takes over then. And we end up with some recommendations, but maybe they're not recommendations anymore, given the discussion we had this morning. So just very briefly, you're familiar with this. So we want to link two databases. We do some cleaning and pre-processing to make sure they're in the same format. We do some indexing, blocking, or searching to prevent having to do the full pairwise comparison. So we end up with blocks, and then we compare records within the same blocks. The comparison, I'll talk more about this on the next slide, is generally based on approximate string comparison. So we compare the Smith and the Smythe and the Johnnies and the Johns because we have typos and variations. So out of this step here comes one or more similarities between records. It could either be a similarity for the full record, or it could be a similarity for individual attributes or fields. And then we do a classification, and depending on the classification model used, we want to have matches. So these are the pairs of records where we believe they're the same entity or person. We have the non-matches. These are often, the ones which have a very high similarity. We have the non-matches, pairs of records which are different people or entities. And then with certain decision models like the traditional Philippian Santer, we have potential matches. So we're not sure if they are matches or not. And then we can either do a clerical review, which potentially flows back into a classification model. And at the end, we want to evaluate how good the linkage is. And that's what we're mainly going to talk about. So I'll give a bit more information about the comparison step and what we assume the linkage is. And then we concentrate on the evaluation. So we want to compare a similarity between two records, and we do this generally attribute by attribute. And as I mentioned before, this is often, these are often approximate string comparison functions. So we have two strings. This can be names, addresses, even dates. I guess you could look, or postcodes can be strings, telephone numbers can be strings, social security numbers, credit cards. These are all often seen as strings. And we want to find a similarity between those. And often that's normalized, so a similarity of 1 means two values are the same. A similarity of 0 means they're completely different. So Peter and David would have a similarity of 0. And strings which are somewhat similar have a similarity in between. And I'll just give you two examples of some of the most commonly used string similarity functions. One is based on substrings qgums, the Chaka similarity. So we convert our strings, Peter and Peter as an example, into substrings. So we have a sliding window. We extract qgrams, so here q equals 2. They also are known as n-grams in natural language processing. And then we basically calculate the set intersection and divide it by the set union, and that gives us a similarity. So the more qgrams two strings have in common, the higher the similarity gets. And this is actually the basis of much work also in privacy-preserving record linkage, where we convert these qgrams into Bloom filters and then use those. Another commonly used string similarity is edit distance. So here we basically count the number of character inserts, deletes, and transpositions or substitutions which are needed. So in a nutshell, it's basically how many keys roughly we have to type to get from one string to another. It's not exactly the same. So this is a distance. So the more changes I have to make to go from one string to the other, the larger the distance is. So we convert this into a similarity basically as 1 minus the edit distance divided by the maximum length. So this, again, always gives us a value between 0 and 1. And again, the example of Peter and Pedro has an edit distance of 3. I substitute the P with a D. I delete the E, and I insert the O. So we have an edit distance of 3, and therefore a similarity of 0.4 in this example. And there's often different ways of how these edits can be done, but it's the minimum edit distance between two strings which we are using. So based on these techniques, we get a similarity between 0 and 1 for different attributes. And then often we assume that we now either sum these similarities together over the different attributes and then normalize. We might also add weights. So we might say, we do this later on, we might say that surname is more important than first name. So we might give the similarity of surname double the weight, or the weight of gender, which is 1/4 being the same, 0 being different, might have less information. So there's weighting schemes. So now everything from what follows on now, we assume we have a binary classification. So we don't have the class of potential matches. So we only have matches and non-matches. So what's sometimes being done, and again, we simplify a lot here, that we have a single similarity threshold between 0 and 1. And all the record pairs which have a record similarity above this threshold, we classify them as a match. And all the records which have similarity below this threshold, we classify as a non-match. That gives us the binary classification. It's all very standard things from so far. So based on that, well, we also have in the evaluation, in order to be able to calculate linkage quality, we need a ground truth, so a gold standard. So we need to have a data set where we have true matching pairs and also true non-matching pairs. Otherwise, we cannot calculate any quality measure. The true matches are pairs of records that refer to the same entity, and true non-matches are basically pairs of records where we know that they don't refer to the same entity. As a side note, in practical applications, if you ever work with linked data, then it's very difficult often to get such truth data. And often it's being generated through the manual clerical review or manual assessment of linked pairs. But we assume in everything which follows that we have such a ground truth data set available. Okay, so what are the 4 outcomes? And so we are familiar with this. So it's a binary classification. So we have 4 outcomes. One is a true matching record pair is correctly classified as a match. That's what we call a true match or a true positive. A true matching record pair is wrongly classified as a non-match. It's a false non-match or a false negative. A true non-matching record pair is wrongly classified as a match. It's a false match or false positive. And then a true non-matching record pair is correctly classified as a non-match, as non-matching, which is a true negative or a true non-match. That's the same kind of 4 values as you get in a binary classification scenario. Now, important aspect is that record linkage is normally a very unbalanced problem. So if you think about, we have 2 databases, the comparison of most records are going to be true non-matches. That's kind of quadratic, right? So even if we do indexing or blocking, we often get many more non-matches or true non-matches than matches. That's important, right? So the number of true positives is generally much, much smaller than the number of true negatives. And we can actually estimate what the number of true positives could be if we assume that the 2 databases don't contain duplicates. So if each database has 1 record per entity, then we know that the number of true matches has to be smaller than the size of the 2 databases. But if I have a million records here and a million or 500,000 here, then I can only get 500,000 true matches maximum if there's no duplicate. So that would be a 1-to-1 match. Okay, so this is just a slide to kind of help the following, the plots which come later in the presentation. So we did experiments. Basically, we used 2 data sets where we know the truth, and we've calculated linkage quality. So the first one is Cora, which is a commonly used bibliographic data set. So these are machine learning papers has been compiled more than 15 years ago by a group of machine learners in America. It's a rather small data set. It's only about 300 records. It corresponds to 112 entities. So 112 machine learning papers. They have different name variations. They might have slightly different conference or journal descriptions and things like that. So we link them. So it's actually a deduplication process. We have roughly 300,000 record pair comparisons. Again, the class imbalance here, and that was with some form of blocking. We say that for every true match, we have about 16 true no matches. So that's not too bad. It's in other cases where it's 200 to 1 or even worse. The second important is that, so what we did is we compared author, title, venue using that QGAM-based Jaka similarity and the year using edit distance. And I guess the edit distance, there's no insert or delete, it's just substitution. So in the results plots later on, we're going to give different weights to these similarities to simulate different classifiers. So for example, one would be we give the author similarity twice the weight and then normalize into the 0, 1, into 1. The second data set is what we've been using for quite a while. It's the North Carolina voter registration database, which is unbelievably publicly available on the web. As I've seen, there was actually a news article last week that the FBI is currently investigating a breakage into another voter registration database from another American state. When I read this, like, good. But this is really, it's a public FTP server. There's no disclaimer. You can go and download all the records of every voter in North Carolina. Names, addresses, and more details. I think I better talk about this offline. It's being recorded. So this is has something like about 8 million records. We've downloaded this every 2 months, so that allows us to kind of do temporal linkage. And for this example, or for this experiment, we extracted subsets of roughly 200,000 records each. They contain more duplicates than the whole database, because most people don't change their details over 2 months period, so they're exact duplicates. So we remove many of those. So again, that leads to like 3.5 million record pair comparisons. We have 27 non-matches to a match. We used a specific name matching string similarity, which some of you might be familiar with, Winkler, first and last name, street address, and city were again the similarity calculated based on Jaka, and for age we used the edit distance. And yeah, for each of these data sets, we show later on 4 different weighting schemes. Okay, so a few more slides before I hand over to David. So how do we calculate quality measures? So here we have our error confusion matrix, or whatever you call it. So we have true positives, which are, so the columns here are the true link status. So we have matches and no matches, and the predicted the predicted status are the rows. So we have the true matches, the true positive, the false positive, false negative, and true negatives. In classification, if you have a balance problem, then accuracy or 1 minus error rate is often used. So that's basically summing the diagonal divided by everything. And interestingly, until about 10, 15 years ago, this has still been used in record linkage, at least in some computer science papers. But of course, because Tn is a very, very large number, it's very easy to get 99.99% accuracy by saying nothing really matches. That's not the point, right? So accuracy is not suitable for record linkage because of that class imbalance. And nobody's really used this for a long time. So instead, what papers are measuring is often precision and recall. So these are measures which are commonly used in information retrieval to measure the quality of results from search engines. So basically, precision is the true positives divided by the true positive and the false positives. So basically, how many true matches have been, the proportion of compared record pairs classified as matches that are true matches. So the number of the ones we have classified as matches, how many are correct. And recall is the column here, so it's basically, again, the number of true matches. So how many true matches have we correctly classified as matches? So this is something which has been used, always being used in many, many papers in record linkage. So there's one way how we can combine them, and again, the idea is that we want to have a single number to characterize the quality of a linkage approach, a linkage method, and often we use the F measure. The F measure has been used again in many papers, which is the harmonic mean. So 2 times precision recall divided by precision recall, which you can reformulate a little bit here, and that gives us this equation here, which basically 2 times the number of true matches divided by the false positive, the false negatives, and 2 times the true. So it's basically these 3 cells of the matrix here. And I just got because we're looking at who has actually started to use the F measure. I just got from an information to a colleague. He sent me a book from 1979, which seems to be the source of the use of the F measure, right? So yeah, and I think that's probably now my part, and I'm handing over to David.
Okay, so this is where we just got to. Laser pointer.
At the top.
Oh yeah, there. Yeah, so this is how Peter just ended. And what I'm doing now is rewriting it. I'm just reformulating it. And you can see this was precision. That was the ratio of precision that Peter defined. This is the ratio of recall that Peter defined. So in fact, this F ratio, which is a harmonic mean, can be expressed like this. Now, before I go any further, let's think about this F ratio. It's a harmonic mean. It's an average of precision and recall. We've got these 2 measures of performance, precision and recall. They're different things. We want to combine them to produce a single numerical measure of performance so that we can compare different methods. And one suggestion has been the harmonic mean, the F measure. But before we even start to combine them, I'd like to pose a question, and we welcome comments or criticisms and so on, because this is very much work in progress, as Peter said. Precision and recall are like conditional probabilities. And they're sort of complementary conditional probabilities. One's the probability of A given B, the other is the probability of B given A. And what we're talking about here is combining them, which from a statistician's point of view makes one shudder. They're different things. It's even worse than apples and oranges. So there's a fundamental question there about whether you should try to combine these very different kind of probabilities. It's not like comparing sensitivity and specificity that people do when comparing classifiers in other contexts. So there's a question there. Nevertheless, I'm going to assume that we still want to combine them and move on. And what we've got here, so this is the F measure, and I've now pointed out that one can reformulate it like this, which is a weighted sum. It's an arithmetic mean of precision and recall, a weighted arithmetic mean of precision and recall. So the harmonic mean can be, for 2 things, can be rewritten like that. And the weight that one's giving to precision here, little p, is just given by that. So this is the first observation. The harmonic mean, I don't understand we don't understand the original motivation for why people thought, aha, we want to combine these 2 things, we'll use a harmonic mean. I don't know where that came from, and I think, personally think a much better way to think of it, since you can reformulate it, is that it's a weighted mean. You will decide how much weight you want to put on precision, how important that is to you, how important recall is, and you'll stick them together like this. I think this is a better way of thinking about it. Now, the question is, what weights do you use? So let's first look at the weights used in the F measure. This is the weight given to precision in the F measure when you re-express it as this weighted arithmetic mean. This is the weight 1 minus p that you give to recall. This is just that little table again. Now, the first thing you notice is about, let's focus attention on this weight, because the same argument applies to this one, obviously. Let's focus attention on this. They involve C and D and B. So that the numbers in there, the weight number, will depend on the algorithm. You build a different linkage system, you'll get a different little table up here, you'll get a different weight P. And what we're suggesting, is that that's nonsensical. if you want a measure of performance, you will say, well, I think precision is twice as important as recall. So you'll stick a weight 2/3 on that and 1/3 on that and combine them like that. It's not what the F measure does. It lets the weights depend upon the particular method. It's like measuring people's heights and using different rulers for everybody you're measuring, you know, or using different units or a rubber ruler or something. It's, I'm going to say, nonsensical. And yet the F measure is very widely used, not just in record linkage, but also very widely used in information retrieval. So our argument is that this is silly. So how can we solve this? Well, to make a fair comparison between methods, the weight that you apply to precision and recall should be a function of you, the researcher, what you're trying to do, and the problem. It shouldn't be a function of the method you happen to be using. That's just silly. So to make a fair comparison, the weights have got to be the same for all of the methods being compared for a particular problem by a particular researcher. And what we've written here is the ratio of the two weights P over, and you can rewrite it like that. It immediately follows. Now, the numerator here is fixed. The number of true matches is fixed for a particular problem. There is a certain number of true matches. What isn't fixed is the number of predicted matches. And by varying the similarity threshold, you can vary the number of predicted matches. It's like moving, I go up into this table, it's like moving the sort of dividing line here. You vary the threshold, this line moves up or down, making these two smaller or larger as you move it up or down. So in this little ratio, the numerator true matches stays fixed, but the denominator changes. So varying the similarity threshold is equivalent to varying the weights, is equivalent to varying the number of predicted matches. They're all equivalent to each other. Now, as I've just said, to make a reasonable comparison between different linkage methods, you've got to use the same weights. So we've got to use the same P, we've got to use that same ratio. So since this is fixed, that means we've got to use the same number of predicted matches. That means for each of the methods we're comparing, what we're going to do is choose what we need to do to make reasonable and fair comparisons, is choose our similarity thresholds for the different methods so that they produce the same number of predicted matches. Anything else is inconsistent and irrational. I'm coming up with, you know, silly, inconsistent, irrational, stupid. So we've got to choose the similarity thresholds for the different methods so that the number of predicted matches is the same for all the methods being compared. And you can think of it other ways as well. And this is what I just said. If you don't do that, failure to do that means we're weighting precision and recall differently for the different methods. Now, the different similarity methods, Peter defined a couple, Jacquard's similarity edit distance, you know, there are others as well. They're fundamentally different, they're incommensurate. What this means is that if you plot a graph of F, the F measure, against similarity, they're not really related to each other because the similarity measures are different. It makes no sense to superimpose one on the other because the horizontal axis is different. And here's an example of the sort of plots you see all the time. We've got F measure, perfectly fine, and then we've got our similarity threshold. We've got the F measure resulting from different choices of similarity threshold for 4 different curves, 4 different choices of similarity measure. In fact, they're based on different variables, 4 different similarity measures. And what people do is look at these curves and say, aha, the green one, whatever that is, Peter can tell you what it is. The green one generally gives a higher F measure for most values of the similarity threshold. Maybe around here it doesn't, but for most, so the green one is better. But I've just said that the 4 curves have different definitions of similarity, so that the fact that they are plotted on this common axis is irrelevant, really. It's just a coincidence. We can transform that axis. In fact, and indeed, only the order matters. To be able to compare them, what we need to do, I've just explained, to be able to compare them, we need to transform the similarity axis so that the number of predicted matches, or the little p-value, is the same. For a given choice of that, for a given choice of weights that you're going to put on precision, equivalently for a given choice of number of predicted matches, then it's legitimate to compare the F values, the F measure values, at those choices. Now, I just said that the similarity measures are different. They're non-commensurate. They've got different definitions. They're not related to each other. And this plot shows you the relationship between the number of predicted matches and the different similarity measures for the different similarity measures. And you can see, first, it's a nonlinear transformation for all of them, but secondly, and more importantly, these curves are different. The transformations are different. Now, if we took those transformations and went back to this curve, and we took the transformations and applied them to this horizontal axis, then we could compare the curves, because then any value on the transformed horizontal axis would result in F measures which legitimately could be compared. And guess what? That's what we're going to do. So here we are. We've got the number of predicted matches, and we've got F measure on that. And there are a couple of things. First, it's now you can compare these. I can take a particular number of predicted matches, and I can compare the curves, compare the F measures at that point. I'd also like to draw your attention, I'm going to come back to this, to the fact that the curves cross. What that means, you can only just see it on this plot. We're going to talk about that in a minute. But what it means is that to the left of the crossing point, one method is better, and to the right, another method is better. But first, what I've got here is number of predicted matches on the horizontal axis and F measure on the vertical axis. And as I said a moment ago, that's perfectly reasonable. I can say, for this number of predicted matches, the F measures are all going to be legitimately compared, and I can look to see which ones are better. Can't see much from that, so oops, here we are. Number of predicted matches is monotonically related to P, the actual weight, or that weight ratio, P over 1 minus P. So instead of the graph I just showed you, instead of this graph, I could put P or the ratio on this axis, and that's what I've done. There's the ratio. I've deliberately chosen the ratio first because if I plot P, things are much clearer. You can now see what's happening. The same argument applies. What this tells me is if I think the relative weight I want to put on, the weight I want to put on precision is 0.4, and on recall 0.6, from this curve I can legitimately compare them, and I can see that the green method, the linkage method, indicated by the green curve, is the best method at that weight. And I can also see that if I think that weight should be applied to precision, no longer is the green, the curves have crossed over and I can choose. But the point is, from this graph, I can make legitimate, coherent, consistent, sensible, not silly, comparisons. So back to the crossing curve, this is the point I just said. One method, it means that one method is superior for some choice of weights and another method is superior for another choice. We've got a second, more complicated example, and Peter can explain why this curve has got such curious shapes. The first graph, the first data set we looked at was the other one, and it produced nice results. This one is more complicated, but exactly the same argument applies, because the argument I'm putting forward is not an empirical argument. It's not based on data analysis. I'm not saying it's a fundamentally theoretical thing, pointing out flaws in what's done at the moment. So that's the similarity threshold on the horizontal axis against F again. Similarity thresholds, not legitimate to compare these curves because of the arbitrariness of this similarity threshold. We need to transform it so that we can. These are the transformations, nonlinear and different for the different similarity measures. That's what you get if you get number of predicted matches on the horizontal axis, and then the ratio again. Totally bizarre. Peter's going to tell you why this is. Totally bizarre, but then we get a relatively sensible plot if we plot P here. And again, the same interpretation. P is the weight that you want to put on precision, and you can choose whatever weight you want and then decide which method, in terms of the F measure, is the better linkage method. So this is where we've got to. The F measure can be used to compare linkage systems, but for a fair comparison, you've got to use the same weights. And best way to think about that, I think the best way to think about that is that you have to choose your similarity thresholds so that they predict the same number of pairs belong to, are matched. Okay. Now, I haven't told you what weight you should use on the horizontal axis. And the short answer, the reason why I haven't told you is because that would depend on you, that would depend on the problem, and it would depend upon your objectives in that problem. And so for any particular research problem, it would be nice if instead of people just saying F measure with the weights which happen to come out of the method which were being used, so it's fundamentally wrong, they actually forced particular weights and said what weights they were using. Then you would know on what basis they were making the comparisons. And that's really what I'm saying here. Ideally, you should make the choice based on on what your objectives were for this particular problem. But I've worked in the parallel, I've spent 30 years working in the parallel area of evaluating classification rules, and I've spoken to endless doctors and financiers and all sorts of things, trying to get them to give me cost values, which is analogous to the weights. And basically, it's extremely difficult. They can't, even in an area like finance, where you might think it's related to something easily measurable. So this is an ideal, and personally I think when people are writing papers evaluating rules, comparing rules, saying this method is better than this one or whatever, then they should say, I think this is important, and actually give a result with weights. But I think perhaps in addition to that, we should also give some conventional weights, which then everybody could look at to compare. But these are conventional, they wouldn't necessarily be appropriate for any particular problem or for your objectives. But equal weights is a nice and obvious sort of convention that people might be happy with, this saves them having to think. And that of course is equivalent to choosing, these are the weights, to choosing them so that these are equal, and so it boils down to making it equivalent to precision equals recall. So you would force precision equal to recall and report the F measure based on that. There is another possibility, and this is not to choose a particular weight, P, which is this thing, but to calculate an average over a distribution of possible weights that you thought might be appropriate. I haven't seen that done. The reason that I'm suggesting that as an alternative is because something, well, exactly the same sort of idea is applied in evaluating classification rules in something called the area under the ROC curve. Can I just ask, how many of you are familiar with with ROC curves or area under the ROC curves? I would guess all of you are. Okay. Now, as I said, I've done a lot of work on evaluating classification rules. I've even written a book on it. Oh God, how boring. But it's the same sort of problem. We've got two classes. I'm talking about two classes. We've got a distribution of scores. They're like similarity measures in what I've just been talking about for class 0. Distribution of scores for class 1. We're going to put a threshold on this score continuum, and anything to the left we're going to classify as class 0, anything to the right as class 1. So we produce a 2x2 misclassification table in just the same way. So it looks like exactly the same sort of structure. Now, I'm going to gloss over this slide because this morning we decided that this wasn't quite right, and there are very strong, this is where I said it looks like it's similar, but it isn't. But this morning we decided it was, so I'm not going to let you read that anymore. This is work in progress. Doesn't affect what I'm going to go on to say. For calibration, for classification rules, you can calibrate them. What does that mean? What it means is if I plot a graph of score against, on the vertical axis, the proportion of objects with that score which belong to class 1, then I can apply a nonlinear transformation to my horizontal axis so that for a particular score, 0.8 say, the proportion of objects which belong to class 1 is 0.8. So that the score is then calibrated. There's a definition of it up there. For classification rules, it's obvious and immediate that you can do that. It's a little bit more subtle for linkage systems, which is what we've spent this morning talking about. But I'm going to assume now that the scores are calibrated. They've been transformed so that any particular score, 0.9, means that 90% of objects with that score, with a score of 0.9, belong to class 1. Okay, here's a receiver operating characteristic curve. It is just a plot of the CDF, the cumulative distribution function for class 1 on the horizontal axis against the same thing for class 0 on the vertical axis. Remember my little plot, class 0 distribution, class 1 distribution. What I'm going to do is imagine moving my classification threshold along. Anything to the left I'm going to classify as class 0, anything to the right as class 1. So as I move my threshold along, first I find lots more things being classified as class 0, and then gradually class 1 begins to catch up everything to, well, these are cumulative distributions, so we get a curve shaped like that. This is a receiver operating characteristic curve. It's very widely used. I just want to, yeah, okay. And the area under the curve is a measure of classifier performance, which is very widely used. Here it is. It's just the area under the curve. It's just the integral. This is just the derivative of d capital F1t. So this is just the area under the curve, definition of it. And you can see a nice intuitive interpretation of this. It's what proportion of class 0 points we get right on average, because they're lower than the threshold, the CDF of F0, lower than the threshold, on average over this distribution of class 1 scores. The fact that this looks asymmetric, sort of unbalanced in terms of F1 and F0, is just an illusion. You can easily, that's what I've done here, you can easily reformulate it. So whichever way around you put it, it's a measure of performance. It's called the area under the curve, and it is an extremely widely used measure, about 6,000 papers. It's used in medicine, it's used in all sorts of areas, credit scoring, speech recognition, all sorts of areas. About 6,000 papers a year use area under the curve to summarize classifier performance in different contexts. And it's rocketed in recent years. So it's extremely widely used. So what I'm trying to do is drive home the sort of importance of it. And there are various interpretations of it, various intuitive interpretations. I just gave you one. It's the average proportion of class 0 points correctly classified if you average the classification threshold over the class 1 distribution. But here's the one, the interpretation which is most widely used, which is most usually stated. It's the probability that a randomly chosen class 0 object will have a score lower than a randomly chosen class 1 object. It's like the Mann-Whitney test statistic in non-parametric statistics. And there are other ways of looking at it. I think this is a useless sort of way of looking at it from the point of view of classifier performance, because you don't get objects coming in, one from each class, in matched pairs. So I don't think that. I think a much more useful way of thinking of it is the average proportion of class 0 points correctly classified, where you're averaging over the distribution of class 1 scores. And as I say, you can also put that the other way around. But you can put it, and I think I've put it in other ways here. I won't go into that now. Now, this is all very well. I've defined area under the curve, and it seems to have a nice, simple, straightforward definition. Average proportion of class 0 points you get right. Average proportion of all of the points you get right, another way of looking at it. But what are we averaging over? I sort of glossed over this. We're averaging over this distribution. And where does that distribution come from? That's the distribution of class 1 scores, which depends on the particular method you're using. You would get a different distribution of class 1 scores if you used a different classification, or if you used a neural network instead of logistic regression or a support vector machine or something. So you would be finding the average proportion of class 0 you get right, but averaging over different distributions. You see what's happening here? We're back to the rubber ruler thing. We're comparing different methods using different instruments. It's nonsensical. I've put it different ways here. It's like saying if method A, logistic regression, were to be used, then we would be very likely to choose probability 0.9 as our classification threshold, whereas if a support vector machine were to be used, then we'd be very unlikely to choose 0.9. This is silly, because this 0.9, the threshold you choose, should come from what you're trying to do, from the problem and your objectives. There we are. The threshold is the property of the problem, not the classifier. It shouldn't depend on the instrument you happen to be using. So I've sort of summarised it here, using area under the curve, or the Gini coefficient, which is which is a simple linear transformation of the area under the curve, which is widely used in other contexts, is equivalent to using a measuring instrument, which depends on the thing being measured. I think I'm going to stop there. I could go on to, there is more. Sometimes these things are used in screening, where you say, I'm not going to put a threshold which says, if the probability of belonging to class 1 is bigger than 0.9, then I'm going to classify as class 1. What people do instead, sometimes they're interested in identifying the top 10% of the population, because they can investigate those in more detail or something like that, in medical screening, for instance. That problem is slightly different, but it also has an issue, which I'm going to skip over. I can go into it in detail if you like. But that particular, using the area under the curve with that, is equivalent to saying you think it equally likely that you will want to assign to class 1 any proportion of the population of objects. So you might, in screening, you would normally say, well, look, I can afford to investigate in detail to give very expensive medical tests to 10% of the people screened out. So I'll fix it at 10% or 5% or whatever. What you will not say is it's equally likely that I want to screen out 99% and 1%, but using the area under the curve is equivalent to saying that. So the other point was, when it was simple classification, it was foolish. Here, it's just totally unrealistic. I'm going to skip over that. And I don't know if you want to follow up on those other slides, or whether we should stop now.
Are there any comments or questions? It depends whether you want questions first and then you want to have a
Well, we only got 3 more slides.
Yeah, they're a bit sort of peripheral, came out of this morning.
Explain a little bit more about these weird curves. But I think if they're general questions or comments.
Yeah, and criticisms, I mean, attack us because I'm attacking everybody. Foolish, 6,000 papers a year, nonsense.
I have a very minor question on the integral suggestion, which was on slide 30 something. I don't know if you can. No, a bit further.
Further forward.
A bit more. So the capital P and R don't depend on small p, right? They're different things.
Precision. Ah, right. Well, okay. I think this is a good point. I think maybe my slides weren't very. What I'm saying, they will depend on the. Yeah, I think we'll pick a particular threshold that will give us a precision and recall, and then we'll weight them according to some weights. You'll say, I think this is 10 times as important as that, but you won't be sure about the weights you're going to use. So that's why we've got this distribution.
But into capital P. So when you integrate, is capital P a function of small p or not?
I think you could do it either way, couldn't you? I mean, I was thinking.
The way you have it.
Yeah. Well, I don't know if I have it. I mean, you're right. I could say that I'm interested. The way I have it here, in this particular slide, different from the others, I think that's a good point, is they're not related. Small p and big P aren't related. What I'm saying is I want a weighted sum of precision and recall, and I in this particular slide, I don't know what the weights are, so I'm going to average over this distribution. But let's make this a delta function. So I'm talking about one particular little p. Now I think precision is 10 times as important as recall, so I'm going to weight that factor of 10 and factor of 1. Now I want to choose. I might choose a threshold so that I can optimize that weight. I can choose precision and recall to optimize that weight.
Yeah, if capital P and R are not dependent on the small p, then you just have a weighting of P and R by the expectation.
You do. It's a weighted sum.
Back to just some sort of averaging.
It does. Exactly. But that's really my point. My point is that the F measure is equivalent to a weighted sum of weighted arithmetic mean of precision and recall. But the weights vary. The weights are arbitrary. They're a function of precision and recall. It's nonsensical. Whereas this one, exactly as you say, it goes back to something very simple and makes sense. And you know, if you think precision is 10 times as important as recall, we can just use it. So what I'm saying is that the method being used, the F measure, isn't appropriate because the weights vary from method to method. If you fix the weights, which is what you should do because you think precision's 10 times as important as recall, that's right.
In a Bayesian way, that's sort of like you put down a prior on
It is,
on
yeah.
distribution. And then is the F measure something like a bit like an empirical base, because you're kind of basing your estimate of, if you think of P as a parameter, and you're basing it on the data, right? You've got
The F measure just uses a delta function for P here. It's just the average, the weighted average. It's not, the F measure isn't an integral like this.
You're right, sorry, yeah, no, just the point estimate for P. which is
Exactly,
based
it's a,
on
yeah,
the function of the
yeah.
algorithm.
But as you vary the threshold so that precision and recall vary, so also does the weight vary, which is silly because you should decide how important you think these two things are.
You have no control over it, basically, as a result, in using the F measure.
Yeah, exactly,
That's
exactly.
That's a good point, yeah.
That's, yeah.
And minor comment which probably will not help here. So sometimes when you decide which average to take, the question is, what do you have in mind? So, if I recall correctly, when do you want to take the harmonic average?
I'm glad you asked that because
I think, just to finish, so I think the answer is, suppose you're traveling part of the time in one speed and another part in another speed.
Yeah.
Now you want to know what would be the average speed to cover the same distance at the same time, but at a fixed speed, and the answer is the harmonic mean.
exactly. Yeah.
So I don't know if here there's a way of thinking, what is really what do I mean by the average?
That was exactly the sort of comment or suggestion I was hoping to get from this seminar. We don't know why people chose the harmonic mean, and it is used in that sort of situation, where really, in some sense, you ought to be talking about the reciprocal of whatever it is you've measured, rather. But that didn't seem to apply here, because really you've got these two rather, two opposite conditional probabilities. So
I agree. That's why I said I don't think it'll help.
oh, right, yeah. Okay, then
There's no speed
what I
here.
wanted from this, well, I suspect there isn't an answer, but one reason why I was very keen that we should give this talk was to see if anybody had got any suggestions why people might think that combining probability of A given B and B given A using a harmonic mean makes sense.
So my question, which might be slightly naive, is how does this relate to measuring under the area under the precision recall curve?
Yeah. So what are your axes?
Precision recall.
Just precision recall.
It's also more recently there has been papers
But it
which
can
has
be,
done that as well, where
yeah.
you plot precision against recall and you get a
And you're getting the area under the
curve.
Ah, okay.
and then higher the better, is that right?
That's what
Excellent.
the
I don't
idea,
know.
yeah.
I'll follow that up.
That's also you have to, I think of this right at the beginning, but then kind
Yeah,
of
yeah.
got sidetracked. So.
I mean, for classification problems, the ROC curve I described, there are lots of other curves people use, but in some sense they're all equivalent to it. Sometimes they're quite obscure equivalences, but nevertheless. So my guess is that, well, because you're integrating, so how does this relate to the area? Yes, excellent question. Yeah. Thank you.
The general point I noticed is very basic, really, I suppose. It's just that I noticed that true non-matches, I think, was D? I'm not sure, one of them.
B,
So
yeah.
the thing that you say is just so often, that's never appearing, I mean, in your, in these calculations. That just because they If they're always such a large number that
That's
it just distorts everything.
Yeah. I mean,
I think
that's not why I think it is because, you know, precision, the probability that amongst the ones you predict as matches, that it will be a real match, and then the complementary thing, the ones that probability amongst the ones which are true matches that you will predict. You know, those two measures by themselves, perfectly reasonable, and indeed very widely used in other contexts, perfectly sensible. Neither of them involve this fourth cell of the table, and one can live with that, but then sticking them together. But other ways of evaluating classification rules anyway, you know, we'll look at the, not the, where's my little table? I'll go back to your table right at the beginning, I think. Have I gone too far? Yes. Okay, so this measure looks at conditional probability there and combines it with the conditional probability there, omitting this cell. Other methods look at combine that conditional probability with that conditional probability, or that with that. So they include all of the cells and make more sense, I think, because, you know, that D over D plus C, A over A plus B, they're the same sort of animal, so it makes sense to construct a weighted sum or whatever.
The problem with the two negatives is that the number of those depends on your blocking scheme.
That's yeah.
So,
Yeah.
so you try your best to get rid of as many of those as you can before you even start comparing.
I guess the information retrieval, I think we mentioned this right early in July. So the information retrieval, we actually don't know the number of true negatives because you don't know how big your collection of documents really is, right? I think that's why.
That can be the same in linkage as well. If you don't know how many of your cohorts you're going to link to the death record, for example, you don't know how many people die, so you don't know how many.
Because
See-
the database is a sample of the population.
Yeah. But from my perspective, I don't see. I come in at when this table's been created in some sense. Peter creates it, and then I come in, and I, in some sense, I'm not. That's not a problem for me. I don't care how you got to this. All I'm interested in is once you've got there, oh, they use that. That's silly, you know. So from my perspective, the fact that different blocking methods or whatever you might not know how many there are in this cell or whatever. I mean, maybe that's an argument for not using the conditional probabilities like this, because you can't calculate one of them. I suppose it's just possible that that's why they came up with combining these two things.
Is there some coherence here? There must be, I suppose. If you hire in both, then you'll obviously have a better criteria, won't you? That has to be the case.
Yeah,
You've got
yeah.
some simple things that you can just make sure that.
Well, I have seen an argument that people like the F measure because it's shifted. It's an average, but it's nearer to the smaller value. But I mean, if you're interested in that, why don't they just take the minimum of the two, which seems to me, that seems sensible. So, yeah.
An association which may or may not be relevant. So this is a little like the famous FDR, which, do you know what I have in mind? The false discovery
Oh,
rate.
false discovery rate. Yes, it's tied into
And
it.
false discovery rate. So if you decide, let's say to make some sort of an analogy, that a match is a discovery, so FDR would look at the number of true matches or false matches divided by the total number of matches. So it doesn't cover both aspects.
That's right.
But,
Yeah.
but the interesting thing is that the rules there, so what you're doing can be compared to testing hypotheses. Each pair, you're testing the hypothesis.
Yeah.
You're using a different way, but
Yeah.
you're testing the hypothesis whether it's a match or not.
Yeah.
And in FDR, it's not a simple threshold. The rule is
Yeah.
more tricky.
Yeah.
I wonder if you can learn anything from there.
Yeah. I mean, what's interesting about this is that all of these very different kinds of problems produce a table like this, and then you're trying to summarize it or extract meaning from it. And I think the different problem domains have slightly different requirements and so on. So I think your question really sort of, or your point really hits the nail on the head here. You need to think about what it is you want to do. People rush into, oh, I'm going to use sensitivity, specificity, accuracy. That's a nice example because in many problems, accuracy, whether you just, in fraud detection, I've done a lot of work in fraud detection. In fraud detection, in credit cards, you classify every transaction as legitimate because you get a very low error rate if you do that. But of course, that's useless. So I think every problem has its own real sort of drivers, and that's what people should put more focus on, more attention on. And it's not at all obvious to me what driver or attention could have produced the F measure.
So FDR, I think, makes the sensible decision that could also be relevant here, that the number of false matches, the proportion should not be too large relative to the total number of matches that you declare. But my point is that maybe you can learn something also about what to do with the thresholds.
Yeah. Thank you. Yes, that's something we'll look at. Yeah.
This FDR now is the most.
I know. Yeah.
Is the most quoted paper. I think this paper beat Cox model.
Is it more
Really?
Cox now?
Really?
Yeah,
So,
it's really,
yeah.
it's very good.
So just to quote it.
Oh, we should.
Yeah. Big crowd.
Are there any other questions?